Good evening and welcome to the November Walmart Labs DC Meetup. Okay, I'm faking it actually. We didn't record last night's presentation, so I thought I would record a version of this talk for the people that didn't attend or didn't attend remotely. My name's Joe Freeman. I've worked in the big data space for the last, 5 years really. And this is kind of a walkthrough of some of the issues I've seen. A lot of companies want to move from streaming data to big data to data lakes versus using batch jobs. They both have their advantages and disadvantages. There's a lot of advantages to streaming, but there are certain pitfalls that I think people should be aware of when they're making this type of decision. So that's what this talk is really about. All right, so first thing is data lakes are really built on top of Blob store or file storage. If you're used to having databases where you basically have a relational store where they manage all the storage and it's optimized for a certain type of storage. Data lakes really aren't that. They're really traditional meaning the last 10 years data lakes are Blob store. They're basically a file system that you drop individual files on and they can't be appended to. It's not like like I said, like a relational store where you would add additional rows. So to add additional data to one of these systems, you got to lay down files, and we'll talk about why that is kind of orthogonal to the way streaming data actually works. And so what happens is, and data lakes were originally designed for very large data, right? Hey, data is too large to fit in a traditional data store. I've worked places where we had one place where we had 20 petabytes and one place where we had 200 petabytes of storage, and a data lake was the only place to store that. So the traditional data lake, like I said, is built around files. It typically has coarse grain access controls and it has coarse grain retention policies. And we'll talk a little bit about the retention policies and how the way you lay down the data can actually make that easier or harder. So in a lot of cases, what we'll do to make a data lake look better is we will cover it with some other layers. So an example would be Delta Lake, where you basically have Blob store and then they add a transaction log on top of that. So you could stream into the transaction log. But if any of the non-Delta Lake favored tooling needs to talk to it, you end up having to flatten that back out into files again. But the big cloud vendors and Delta and Databricks basically are working to try and work around this problem where the data lake, data storage in the cloud, and really data lakes only work in the cloud because you have pretty much unlimited storage and you have at low cost, right? This is really, the only thing I want to get across here is that this is the way the files are laid out or the way storage works. And so everything we do that is different than that, we have to bend things a little bit. And like I said, that's the reason the lake vendors are actually doing that work. So streaming in 12 seconds, and it won't be 12 seconds because I can't do anything in 12 seconds. Streaming is basically the taking of individual records, documents or records. So streaming is a record or document-oriented format. It is not something you would generally use, although you could. A lot of people don't use it for things like sound files, sound recordings, call recordings, pictures, that type of thing, or a giant mass, a graph. You would end up having to store the graph as a document and send it. So this tends to be, you take individual records from some source. The most common uses for streaming are actually clickstream data from web and mobile apps and log files. Sorry, I'm having coffee, a little bit of a coffee voice this morning. And what happens with streaming is you can have multiple consumers on that stream and each consumer actually processes that separately. So here I showed two consumers, one feeding an application, one feeding a database, and one lake writer putting it to a data lake. And the data lake might be something with, unlimited retention or unlimited data store, that type of thing. So streaming is really taking an individual message and an individual record and sending it. So if you were getting partner data on a daily basis from some commercial partner, or if you're in the federal government, you were getting it from a partner organization, and that came in a batch, a large file, basically you'd have to strip every record out of that file and send them one at a time into the streaming infrastructure, and we're going to talk about why that can be good or bad. Pros and cons. Beautiful thing about streaming is you get continual data updates. You can get near-time fan-out. So there's real-time, batch, and there's near-time. Real-time would be pretty much, sub-second. Depends on your use case. Near-time is I can get it pretty quickly. So the use case I've seen for that is we're taking clickstream data from a mobile app, and 2 pages from now, we're going to make an ad offer on some page. And so we need to get that data into our system. It's not on the same page they're on, but then when they click to some other panel, that's where we're actually going to make a recommendation on something based on what they previously looked at. So that's near time. With streaming, there's no massive full data set processing. So if I were to take today's credit card transactions for a bank or today's credit card transactions for a certain card, and I needed to process those, that's a huge data set in a batch. Although you can get the whole co-location thing and join with it, so you can actually look at where things relative to each other. In streaming, you only got to be able to process one at a time. So if you had, I worked somewhere we did, well, plenty of places now, do 1 million messages a second. I only need enough processing. The individual compute nodes only need to be big enough to process one. If I was going to do it as a batch in 1 second, then I would need a node big enough to process 1 million records simultaneously each second, right? So that changes the scale. And so streaming pretty much has unlimited scale up. You can scale up, you can scale out, but basically you can increase the amount of data you can handle, and you are not limited by the size of the machines. Streaming works well for event tracking and logging. Like I said, click streaming and logging. It's also good for idempotent changes. We'll talk about that. Idempotent is a cool word. And it really means that I can apply the same change multiple times without destroying anything. So example of something that's not idempotent is I made a deposit. And if I didn't take care of that correctly, and of course the bank would do this correctly, but if I were to replay that transaction over and over, I would end up with multiple deposits in my account, right? Okay, so the downside of streaming, the order that the data arrive is not guaranteed. So if you need data to arrive in a certain order, like I create an account, I make a deposit, I make a withdrawal, I close an account. I don't want those processed in the wrong order in a financial system. If I do those in a batch, I can actually just kind of read the batch and process it. If I do it in streaming, they may not come in the same order, and I'll show why. Even when people claim they can, they might not. And duplicate data is possible. So there's no such thing as a commit log for an entire data, for a piece, well, whatever. So it's possible I could have a consumer fail after it has written to the data store, and then it'll run again, and it'll rewrite that data. And because of the way big data works, I could end up with duplicate records, right? If I did it as a batch, I might have more control over knowing what duplicates I have. And blown consumer operations may be hard to recover. I always call this like, how complicated do you want something to be at 2 in the morning when it's not working? So if you have problems where consumers start failing, you'll end up with a continual stream of records that fail until you take those consumers down. You'll have to figure out some way to reprocess those correctly. And you'll also have 1 million messages a second coming in. And you may not have enough storage. Back pressure may cause other issues. Hopefully not back pressure. But so if you have fan out failure, so if I have multiple data syncs going to different places, if one of those starts to have failure and you expect those data stores to be in sync with each other, that can be difficult. Batch jobs, it tends to be easier to reconcile fan out failure because you have basically an entire data set, you know what happened with it. Whereas with streaming, individual messages may succeed or fail. So I could get 1 million messages a second. 200,000 of those in that second could fail because they're a certain type of transaction that came through. But the other 800,000 would have been processed, and then I got to come back and pick up the 200,000. And the 800,000 would have already been consumed, so it might be hard to reprocess that. So another no notion of an actual data set. So if a block of transactions has to happen together, we got partner data on every Friday. And I want to process that at one time so that all of our users are updated at the same time with the partner data. There's no way to do that. You don't have this notion of a data set. The data will be processed. So an architecture's greatest strength is its greatest weakness. The beauty of streaming is everything is processed as it comes in. The downside is everything is processed as it comes in. You have limited data protection in streaming. It has transient storage. So a lot of times people will keep like a week's worth of data, so you can actually do replay or triage on the data stream for up to like 7 days because the data is still there. If you do it with a batch, you keep it around for years. You can always roll back and see what data you actually processed 6 months ago. With streaming, to do that, you end up having to write it to a batch file as raw data, and then you can go back and do it, but that seems kind of weird. So the main plus of streaming really is this compute problem and the fact that you can get real-time or near-time updates. So the nuances, like I said before, uniqueness is not guaranteed, order is not guaranteed. This limited message size, we actually ended up discussing this in the meetup. You're limited in message size. This can be a problem. If you have, a lot of these tend to be fairly small, plus you have aggregated storage. So if I keep 7 days worth of data at 1 million messages a second, or a couple 100,000 a second, or 1 billion messages a second, one place, then you're limited by the message size, right? And so that can be a problem, like if you're taking WAV files or you're taking large complex document. I worked at a place where we were doing telematics kind of data, which is basically where is a car moving on a trip it went on. And we were getting multiple readings per second out of that. And so the size of the data actually kind of partially depended on how far you went. And so it turned out putting that in a message stream could actually be difficult. We were over our size limit. We could be over our size limit, which means you'd get random failures. There are workarounds of that, like a side claim check model. You can either split the message up, but then you have to reassemble it. And because you don't know when all those parts are going to come in, reassembly can be hard. We'll talk about that at the end. Another option is you do kind of like Azure Service Bus did originally. I don't know if they still do that. If you have a message that's too large, they would actually put it, and actually Snowflake does this for large data sets too. They would put the data actually in Blob store, and they would just send a pointer to the Blob store, right? And so the message didn't actually hold the data. It actually went in a Blob store side storage area. Kafka doesn't do that, and other streaming systems don't do that. And then you have schema binding behaviors, and we'll talk about that. So there are some subtleties in streaming. So streaming data can make reliable consumption hard. You can have multi-path effects, right? So if I'm getting 1 million messages a second or whatever from 10 million logged in phone apps, seems like it. Well, anyway, so to consume that, you would end up doing parallel consumers, and you do parallel sharded message streams. So you basically can increase the amount of traffic that can go down your streaming road by adding more lanes. What that means is you can have different behavior based on reading, because you're going to have multiple consumers on those different streams. And depending on how you did the partitioning of that, you either may get a person's data out of order, or you may just get stuff out of order across people or across producers, right? So multiple consumers will actually affect the order data is put into the lake. A lot of times you don't care. Logs, you don't care. Click streams, you may not care. But there may be other cases, especially if you're feeding financial systems, where you may actually care. And there are probably other use cases too. So multiple syncs. This one here, I just wanted to show that the beauty of streaming is you can get fan out. With batches, when different data syncs are actually going to get their data, because you have a scheduled job, or maybe you do micro batching, which is sort of like a halfway between streaming and batching. We'll talk about micro batching later. So the data comes in. I did it here. We had 2 different blocks of transactions or messages that came together. They actually ended up in a sharded stream. So we have XYZ, ABC. The consumers run at different speeds, and the shard consumers run at different speeds. So system 1's got multiple consumers across the shards. It actually processes them. In this case, its consumers were running right on schedule, and it put the first one in each of the shards into my data store in the database. In the second situation, one of the consumers was slow or had a restart. That meant the data on one of the shards was brought in, more of it was brought in before the second shard actually got picked up. So in this case, I have a database with A and X, the leads from the 2 streams. And the bottom one, the cloud store, actually ended up with data on one stream, and the other stream just started to come in. So those will be eventually consistent. Now, based on how fast this is, it may not matter at all. It is possible, though, that could be a problem if you're assuming they're completely consistent, right? There's no such thing as transaction integrity anymore in the cloud, which is a general statement. But I just wanted to point out that you can get this eventually consistent issue, and that may be totally fine. None of these may be showstoppers for you. I just want the goal here is to identify them. So the ideal use cases for streaming are really records that have meaning that is independently of each other. I'm going to fix that. So if records are independent, logs are a great example. If the data is already a natural stream of events and you would have to aggregate it into a batch and then put it back, then it makes sense. So things like flow logs and click streams are great. If the data is too large to reliably batch, if I'm getting a couple 100 million messages a second, or 1 million messages a second, it may be that data is too big for me to reliably batch, or I would have to do multi-consumer batch processes. So in that case, streaming's great because you have unlimited scale up. It's also good in serverless environments. There's a move away from having real machines. I mean, machines running an operating system as the primarily deployment vehicle for applications, right? And so in a serverless environment, you're limited on size. And so streaming use cases are ideal for those serverless environments because the amount of data in memory at any given time is small. Problematic use cases in my mind for streaming are CDC. This is like the thing everybody likes to use streaming and messaging for. I find it difficult because we have an order of operation problem. And also, if you miss a message, the replicated data store is completely out of sync with the source. Whereas with a batch job, if the batch fails, you know the block of related messages that didn't get processed and you can reprocess them. If you do streaming and a message gets dropped or a message gets put on a DL queue, dead letter queue, and other data is brought in, then you've actually processed those out of order, and then some time later you will bring that thing up to date. I've seen this before, and once you get out of sync using CDC, man, it is hard to bring that thing back together. So order being required, financial transactions, seen this a couple times where this is really difficult, especially if you're going to do the multi-consumer thing. Like Kafka, if you're using Kafka streaming, I'm going to use that as an example. The order is guaranteed within a shard, right? What's not guaranteed is that you will process all those in the right order, that some won't end up in a DL queue, or that you won't end up scaling out across multiple shards, and then those transactions might not be in order anymore unless you get all the partitioning right. You got to be smarter to make it work. I'm like brute force and ignorance, so that whole got to be smarter thing, it's great until like you're not smart that day. So if you have an all or nothing problem, if I have a data set from a partner that has all their whatever information, and everybody's partner data needs to be updated at the same time so there's not confusion on the website, and I'm just picking basic examples here, then streaming's not good. If you got to have an all or nothing, then it's a problematic use case. If a data set should only appear when it's complete. So I've seen this before where we have a data with a bunch of sub-transactions in it, and really we only want this to appear when the transaction is complete, or when data processing has been done by another team or something like that. In that case, a batch might actually be better because you can process the entire set of data and everybody's seen pretty much at once. The other thing is problematic use cases. If the sync is a file or blob store, we end up doing batching anyway. So I'm going to show you at the end. We stream into a data lake. It actually ends up being micro-batched. And so you kind of might be stripping a batch down and then streaming it and then putting it into a batch again. I don't know. Does that make sense? Streaming is great. You get incremental updates, but there are some cases that can be difficult for you. Data completeness. This is an expansion on the previous comment. So how do I know if the data is complete? Do I have a completeness issue? I got partner data. I got a file from the state that told me who had paid their withholding tax, and now I need to distribute that across sub-organizations. And we want to know when everybody's been updated. There's really no way to do that with streaming. A lot of people will try record counts. So that's, I got 200,000, and I've seen this before, 200,000 records in this file. We shred the file, we stream it, we load it into the database or data store into the lake, and I got 200,000 records, but it turned out it wasn't all 200,000 records. 10 of them failed and 10 of them duped. So I actually ended up, the count in that case didn't actually help me, right? So some people will inject tracer information when they strip that batch down and then stream it, and then they'll record the tracer information on the backside and they'll know which records didn't come in. But if you think about it, that's a lot of work for something that you probably could have batched. I'm not opposed to this. I'm just telling you, these are the things you got to think about. So we talked a little bit about this before. Finance systems is a really good example. If I require data serialization, CDC is a good example, change data capture, and the other one is finance. Financial transactions it's best if they're processed in order, right? And that's why their historical end of business day accounting may actually be better in a lot of situations. So really, I'm going to talk a little bit about this one. So we ended up with a case because in this case, I've got two streams, two shards in a single streaming system. And in the data lake, I don't care, right? So in the data lake, I'm showing that one of the stream processors is running faster than the others. And so it lays down its records, 1, 3, and 5. And the 2, 4, 6 consumer is either not up or it's restarting, or it's slow, right? And so in that data store, I got 1, 3, and then a 5. And what I really want is 1, 2, 3, 4, 5, 6, right? And because they got sharded wrong, they're in their own substreams wrong, they'll actually get processed out of order. But I need them laid down in the data store in order for like a financial transaction. So sometimes you'll end up having to do a sequence store serializer and then a batch process to load this. So in this case, we got 1 and 3 in the sequencer store, right? 2 didn't come in. I can't write it out. I could write 1 out, but I can't write 3 out because 2's not there yet. And that means I put trace information correlation data in the original message. 2 finally comes in the sequence store. I see the 2. I can write the 2 out because I know I've already written 1 out. I've got 3 in the store and I'm going to write it out. So this is a serializer forcing function, and it's because I needed the data to be written down in order because the downstream processes don't know how to do open account, make a deposit, make a withdrawal, close an account. If the close account shows up first, a lot of systems would throw that as an error, and then you'd open the account, make the deposit, make the withdrawal, and the account is left open because the close account transaction couldn't be processed because it had already been consumed. And I get you could do date sorting with this, but essentially that's forced serialization, right? You'd end up having to store the close account until the previous transactions show up. So that's just something about forced serialization. So I threw this one in. This slide wasn't in the Meetup talk, but we actually talked about it with some questions. So this is the data lake or warehouse argument. So typically in a data lake, sometimes known as the data swamp, we eat everything, no matter what the schema, no matter what the data. We reject actually absolutely nothing, especially in a raw partition, a raw data lake. And then streaming typically tends to be strongly schemaed nowadays. So a lake accepts everything. You can get random accidental schema drift, which is bad and good because it means nothing's rejected. And it'll accept non-square data because basically it's blob store. I got a file system. I can jam anything I want in the file system in any format, and it just works. Greatest strength is the greatest weakness, so that causes some problems too. Streaming tends to force things, and that may be good or bad. And I've worked a place where we moved from data swamp to streaming, and it was amazing. And then we dropped a whole bunch of use cases because the streaming approach actually meant some of our use cases couldn't be done, but the other use cases were handled really strongly. So streaming tends to force record orientation because you have small objects, right, that can fit in the stream. They have hard validation on schemas, so they tend to be registered schema. You know what's in the schema. This is amazing because you know exactly what's there. It makes it hard to do random drift, which is great. It also makes it a little brittle to do drift because the way streaming processors, they tend to, not only do you validate the schema on the way in, the processors tend to assume that data is in a certain format and process it, whereas batch processing tends to just read an entire blob of stuff and write it out, at least for data transfer into the lake. So streaming often has hard validation. This is greatest strength, this is its greatest weakness. Sometimes you'll have quarantine zones. I don't know what happened here. I'm just going to drop it there. That might be if you reject it at the front door, then the producers actually need to be able to recreate all that data. And a lot of times you can't recreate data. So a good example is clickstream. Shape of the clickstream changed. We're getting it from the devices. The schema changed. If I have schema validation, which is great because it means the data lake will be always the same schema, I actually lose all that clickstream data when the shape changed. And I have no way to generate it back because it's not like we're going to go back to the phones and ask people to re-click. And so an example of this forcing schemas is Kafka Avro. The last 2 places I've worked, currently and the one before, we moved to full schema validation for inbound. And that's great for programmers, but it's lousy for being wide open, right? All right. So this is kind of the last subtopic. And the thing here is cloud data lakes are really micro batching under the hood. So no matter what we do when feeding a data lake, our stream data will be converted into a micro batch. Now, if you're running something like Delta Lake where they do transaction logs, they manage this under the hood, right? Or if you're using Snowflake, I'm a huge Snowflake fan, I'll just say that up front. They actually do super small micro partitions, and so they simulate appends by having thousands or tens of thousands of tiny partitions. But the reality is, under the hood, it's still micro batching, okay? Because we have to lay the data down in the way it's stored. So streams and storage style may not match, right? That may not matter. You don't care. The way you're streaming your data or the way it gets organized, that's fine. This can complicate retention or not. It depends on data retention is something that's really immature in the lake, and I need to do a talk about it, I guess. A lot of times people were doing retention just around the data, around the partition, around the file in the lake. And so that implies that the data needs to be co-located with its co-retentionees, right? So that they can all be removed the same way. That doesn't obviously apply for CCPA or privacy, where you got to pull out individual records and remove them. So retention is more complicated. So it may or may not make it more complicated if you lay the data down wrong, because the storage, you're going to rely on storage, like aging of data files, that kind of thing. It may complicate group operations. Do I really need a group of data that needs to be co-located to improve the processing? So this is related to producer and consumer schemas, right? In a lot of cases, as a data producer, I don't care. I'm just going to lay this down in a producer-driven schema. And then if somebody needs to use this data, they're going to convert it to consumer-driven, a consumer-oriented schema. A lot of companies, though, don't have enough staff or enough engineering governance to actually have reliable producer-driven schema to consumer-driven schema conversion. And so the consumers all consume the producer schema directly. That makes that more brittle for them when the producers make changes. It also means that if the data wasn't grouped correctly originally by the producer, then the consumer performance is going to roll off a little bit. And the storage may not match logical boundaries. Let's just look at a couple of these. So everything in the lake is batched. Basically, the way this works is a message stream. The message data is gathered by a lake writer, and they call them partitions in data lakes, right? So like if you're using Avro or Parquet, they call it a partition. So each you can partition by day, right? Like, so let's say I've got a year's worth of data. I'll have 365 partition. Each partition will actually have multiple files in it as that data was gathered. Sometimes you'll do things like my optimal size is 100 megabytes. So every time we get 100 megabytes worth of data, we're going to write out a file into a partition. And so Tuesday's data is made up of 200 files in that Tuesday's partition. When you're streaming, you may take into account time also. So it may be 100 megabytes or 30 seconds worth of data. And so you may end up having to reorganize storage for performance. Because this is a producer-driven scheme, actually the data will be laid down in the lake around how the data came in on the producer, not how you're going to consume it, right? So you can have some impact. I'm going to show you two different multiple streams examples here. This is an optimization. You may not care. I snagged this one in here just because I've seen a place where this was an issue. If I have multiple streams with a single writer, if I wanted that data to be co-located in the sharded streams, like if they were sharded by business unit or they were sharded by region or country or something like that, if I have a single writer to the lake, when I write it out, that data will actually be co-located. So in a given partition, let's say today's partition, and I write down every 10 minutes, I write data out. That each of those files will be a mix of the data from the different streams. If I wanted that data to be co-located by stream, then this multiple writer, single writer, aggregated writer doesn't actually help. I could even have multiple writers here that are doing this, but let's pretend we only have one. And so in this case, the sharded data actually ends up co-located with each other, not necessarily co-located only with its own shard. That may or may not be a big deal. This is mostly an informational session. The last one here is multiple writers. In this case, the data is retained by shard. So this is the opposite situation of the other one, which could also be good or bad. It may be that I want the data to be intermixed by time that it was processed. And so in this case, I'll actually end up with overlapping files for the same time. Again, you probably organize your data in a way this isn't an issue. I just want to call this out. In this case, you'll end up with sharded oriented partitions. And if you change the number of shards over time, you'll end up with different numbers of files in that partition, right? So just be aware of it, that the system under the hood is a batch. And so it is going to lay down files in different orientations based on how your consumers are set up. So that's it. This only took 5 minutes less than I did the other night. So thank you for attending this virtual talk, and thank you for the people that didn't attend. Show up at the next one. There's a YouTube channel where this obviously is up. If you have any questions, just post them on the YouTube channel or send me a note. The basic idea of this presentation was, hey, streaming's amazing. It is what everybody wants to do. There are some subtleties to it and some side effects that may or may not make your data a good candidate for streaming. Thanks for attending.